We're going to look at one more example revolving around the central limit theorem for means. So suppose that test scores are normally distributed with a mean score of 73 and a standard deviation of 4.2. A sample of 24 tests is taken. Question one, first question right here, it says, what is the probability that the sample mean is less than 71? So we're talking about the probability of a sample mean being less than 71. This means we're going to have to use the central limit theorem because we're talking about the probability of our sample mean. Now, this looks initially like kind of a problem because we said for the central limit theorem, we want n greater than or equal to 30. And in this case, n is only 24. So in this case, let me write this down. N is equal to 24. That's not greater than or equal to 30. This seems like kind of a problem for us. However, we have one other thing that we can check here, and that's that the underlying population is normally distributed. So this tells me right here, suppose that test scores are normally distributed. This essentially allows us to bypass the n is greater than or equal to 30. We don't really care what the sample size is, even if it's less than 30. This means that the central limit theorem will apply. We will get to use it right here because our underlying population is normally distributed. So, at this point, we've established that the central limit theorem will work. The sampling distribution of our x bars of our sample means will be normal. So we need to start by finding the mean of the sampling distribution, the mean of our various x bars. Remember, that's the same as the population mean, which they tell us is 73. The standard error or the standard deviation of the sampling distribution of sample means is the standard deviation of the population divided by the square root of my sample size n. So my standard deviation was 4.2 divided by the square root of my sample size, square root of 24. So I want, grabbing my calculator here, 4.2 divided by square root of 24. I ended up with 0.8573. I'm going to give all 4 decimal places just in case I need them. So the central limit theorem says, okay, well, we get to assume that the sampling distribution of x bar is approximately normally distributed. That's kind of the main goal, the main point of it. The mean of our distribution, we said, was 73. So the mean right here is 73. We would like to find the probability that our sample mean is less than 71. So, okay, less than 71. 71 is going to sit somewhere over here on the left. And if we're looking for the probability that the sample mean is less than that value, we are looking for the area to the left here. So first thing that I need to do is I need to find the z-score corresponding to 71. So z is equal to x minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution. So 71 minus, we said 73, divided by 0.8573. So 71 minus 73 over 0.8573. My z-score looks like negative 2.33. So there's my z-score. And then at this point, we can hop over to our z-tables and we can say, okay, what's the area to the left of negative 2.33? So hopping over to my z-tables, let's erase the work that we had earlier. We said negative 2.33. So negative 2.3, here's negative 2.3, which means we're looking at this row. And then the second decimal place is a 3. That's what I'm looking at on top. This is the column that I want. So that means that the probability there would be 0.0099. So this probability, this area to the left, would be 0.0099. Oops, let me write that out so that it's a little bit clearer. This shaded area is 0.0099. And there's our answer. So again, we just have to make sure that the central limit theorem applies, make sure that it is a central limit theorem question, and then find the mean and the standard deviation of the sampling distribution before we can then move on and set up our picture, find our z-score. Next question. This one's going to be really important that we look at because it is a potential point of confusion that we can run into. Number 2 says, what is the probability that a single test score from this population is less than 71? So if you look at these two questions, number 1 and number 2, they look really similar. They're both talking about the probability of something being less than 71. But if I look at this second question, here we're talking about the probability of a single test score versus here we were talking about the probability that a sample mean is less than that. This is really important because anytime we talk about that probability of a sample mean being less than or greater than some value, we probably need to use the central limit theorem to answer that question. Here we're not. Here we're just talking about a single test score, which means that this is not a central limit theorem question. Well, if it's not a central limit theorem question, how do we answer that? Well, we kind of just have to hope in this case that our underlying population is normally distributed. And this is why it was so important that we talk about this way back at the beginning. We know that our test scores are normally distributed, which means that we get to use our regular old normal distribution. So we can draw out our normal curve and we can say, the mean was 73, here 71, and we're looking for that area to the left here. So it's important that when we look at this, we determine that we're dealing with something which is normally distributed. Now, if on the other hand, I go back, if I didn't have this sentence right here, or even if it said, hey, the distribution of my test scores is right skewed, then I couldn't answer this question because I only know how to deal with normal distribution at this point. So it's really important that we verify that these are normally distributed because otherwise I probably can't answer that question with the tools that we have at this point in time. So because this is normally distributed, we can still answer this question, but it's not a central limit theorem question. We said that the population mean was 73. That's why I wrote it in the center down here. And the standard deviation is, we said 4.2. And at this point, this is a question that's really similar to what we saw way back in chapter 4. There's not really going to be any surprises here. So we would start off by saying, let's find the z-score corresponding to 71. So that would be 71 minus 73 divided by my standard deviation of 4.2. So 71 minus 73 divided by 4.2. And we end up with negative 0.4762, actually 48 if we round to 2 decimal places. So negative 0.48 for our z-score, and then we would, of course, go and consult our z-table in order to find the area to the left of that. So let's do that one last time to finish up. We're looking at z equals negative 0.48. So negative 0.48. This time I'm looking, here's negative 0.4. This is our row. 8 would be all the way over here on the left. So our area to the left is 0.3156. So the probability that we're working with is 0.3156. There is our probability. So the thing that we're going to want to pay attention to in these problems, the kind of trick that we might run into from time to time, is are we talking about the probability regarding a sample mean, or are we talking about the probability of a single value from our population? If we're talking about the sample mean, that always means that we're going to use our central limit theorem. We are always using that central limit theorem. versus if we're talking about the probability of a single individual value from our population. That means we are not using our central limit theorem. We're just using the regular old mean and standard deviation from our population, as long as we know that our population